Good morning. Basic agenda I'm going to try to get through is up there. I had questions about branch and bound trees, the one from the homework, but also I've got a couple from past exams to go over. Then, because I expect a few more people to trickle in, I'll go over exam format, then we'll go back into some goal programming review and then general questions. But are there any general questions on chapter 7 stuff before I start that? Okay. So I was asked to go over this homework problem, and then we'll do a couple others like it because these are classic ways of assessing your understanding of branch and bound. They make very good exam questions. Hint. The meaning of a tree is we start with an original integer programming problem. We don't really know how to solve those. So instead we solve the LP relaxation. We cross our fingers and hope. If the solution comes back integer, then we say, hooray, we have an optimal solution to that IP because of that property that the solution value to the LP relaxation will always be at least as good as the value of the IP. Why? Because the LP relaxation relaxes, has fewer constraints. When we fork off two daughter subproblems, that implicitly means the solution to the LP relaxation was not integer value. It scored 120, but if one or more of the decision variables were not integer. So we fork off two daughter subproblems by adding the constraint on this side that one of those variables is less or equal to its round down, and on this side that one of those variables is greater than or equal to its round up. Quick aside, you don't need to know about, there's a lot of smarts that goes into trying to figure out on which variables you branch. And in fact, in the real world, you don't have to branch on only a single variable. You can actually branch on combinations of variables, any linear function on them. Back to our regular programming for an introductory class, we continue this iteratively, and just that process, that recursive process, is an algorithm for solving any integer programming problem. However, it can often take like 10,000 times the age of the universe because these trees can get ginormous when we have more than just a small number of variables. So we like to prune or bound the tree by recognizing that if we know how to do a certain score, and there's a branch that we could explore, but there's zero possibility of doing better than what we already know how to do, why bother? That helps a lot, but still not often enough. So sometimes we add this notion of tolerance for suboptimality, which says, if we know how to do this well, and there's something over there that would take a lot of work, but it would only could only possibly do a wee tiny bit better, we just say, let's not bother. Right? So that's the concept, and we're testing it in terms of how you read this tree. Is this a max or a min problem? Well, as we move down, we're adding constraints. When you add constraints, you can never do better, and you might do worse. So apparently having z go up is worse. So if having the z value go up is worse, that must mean we wanted it to go down. That's how you know that this one's a minimization problem. And always pause and ask yourself that before you go further. Usually I'm nice, and part A of the question asks, is this a max or a min, to remind you you've got to do that? But sometimes I'm grumpy and I don't make that part A, but you should still do that yourself. Make sure you know whether it's a max or a min. The notation here means when we solve that LP relaxation, it had an integer solution. Zip is IPZ. So we know for sure we can get a 160. Right, now let's sort of the problem. Which subproblems cannot possibly contain the optimal solution? So here, the LP relaxation is 190, score is 190. Nothing underneath that node can do better than 190. And in a minimization problem, that means all integer solutions underneath there will score 190 or worse. And we already know how to do better than that. So don't bother exploring further underneath that node. Don't bother exploring underneath that node. It couldn't possibly beat the 160. Which additional leaves could be bounded if the tolerance parameter is set at 10%. that means that any leaf whose LP score is not better than 144, we can also forget about. So we don't need to worry about this one. Yes, if we went underneath here, we might beat the incumbent solution, but we couldn't possibly beat it by more than 10 points. 10 points is less than 10% of the Z. Likewise, these daughters must have LP solution values that are not better than the 150 because they were created by adding constraints. So we don't know those numbers, but they can't be below 150. So we'd also be able to drop 13 and 14. I think that's all of them, because these two both could potentially beat the 160 by more than 10%. And you don't say, oh, don't explore underneath this subproblem, because you already have. So the questions about what you prune or bound are about leaf nodes.
So if we know the leaves under problem number 10 on the right-hand side, right, we know those can't do better than 150, so why wouldn't we just cut off number 10?
Sort of as I said, we've already forked off the daughters of 10, so we might have been able to do that 5 minutes ago, but it's too late. We've already created its daughters. So that question of do we prune or not is only a question that's pertinent for the leaves.
The leaf where the linear relaxation is equivalent. That mean that a leaf or like a daughter of that leaf could have any programming solution that's 160 or that have to be.
No, it is possible that one of those. It's possible that there is an integer solution that does score 160, and so it could be an alternative optimal solution. So in general, we don't at this level sort of ask that kind of question, but in the real world, you could say, do I care about finding alternative optimal solutions or not? And if so, then you would like set the parameter so that I would explore even if it ties. But if all you're interested in is finding an optimal solution, then you could drop the one with the tie.
You wouldn't necessarily cut it out unless you're saying.
Yeah. I think not just the way that I write the questions, but in a standard textbook format, we think of the goal as we want to find an optimal solution or a solution that's within X tolerance percent of optimality. But the variation, like in a more advanced class, second year class, they might say, how would you adjust the standard branch and bound algorithm if you did care about finding alternative optimal solutions? Then the answer would be, when it's a tie, you would not prune. I'll pass that along to Peter so he can ask that of you next year.
When we talk about 10%, are we thinking about 10% of 16 plus and minus, or 160 is already in the 10%?
I don't want you to have to worry about that. Back when I was young and stupid, I tried to make that distinction and it never went well. So on my exams, I will always choose the numbers to be big enough that you won't have to make that distinction. Right. So for those of you who didn't catch the question is, are we pruning everything that is within 10% of this number? Well, no, technically it's not quite that, because that's not Z star. You're pruning everything such that its Z star is no more than 10% of that currently unknown values reach of 160, and that's just a little bit different. You think about it as, is it plus or minus 10%, or are we multiplying or dividing by 1 over 1.1? That's effectively the distinction. And when I used to try to make that point in this class, people just didn't understand the whole thing, gave up and hated, and said they never want to do integer programming again. So on the exam, I won't make it that close. So
for this class,
if I say 10%, you'll notice there's none that are 11% or 9% away.
So the number will be pretty distinct. They're either in that 10%-ish range or they're not.
Yeah. So you're going to prune the stuff that's under 10% of the number that you're looking at, and you'll.
Can you explain, if you already did, I'm sorry, but can you explain again why we didn't look at the 10% above? Like, why isn't it?
Well, we're
10%?
trying to minimize. So, like, suppose I had a leaf out there that had a ZLP of 165. I can trim that even if my tolerance is 0, because nothing under that could possibly beat my incumbent solution I already know about. So we're only interested in possibly trimming things whose ZLP is a little bit better than our incumbent.
So tolerance doesn't mean like accepting what's worse. It means what we're willing to change, or?
Oh, well, backing up to the concept is we permit the computer to stop with a solution that may not be optimal, so long as it can promise us that it is within a certain percent of that, of what is actually the optimal solution value, which we won't know because we're not going to force the computer to work forever.
So, what were the leaves in this problem within 10% that we would do?
1, 2, 3. So the gap here of 10 is less than 10% of 160. And here it's a little bit trickier because I didn't tell you what those values are, but you know they can't possibly be better than 150, so they can't possibly be more than 10% better than the 160.
People are saying there's an issue with the Zoom.
Oh no. Thank you for telling me that's not directed at you. What is the issue with the Zoom today?
Where it's supposed to be showing the classroom, it's just like kind of a weird color.
Okay, I will pause for a second and see if I can figure out what to do about that.
I think that the wrong camera may be selected. I think you just might need to switch to the back camera.
I just pressed a button. Did that help at all?
No.
Bummer. I just pressed another button. Did that one help?
Yeah, now I can see the students.
Who are waving at you. And what you see now is useless?
What I see now is like an orange rectangle, like it's too zoomed in on something.
Got it. Is
Oh, that's helping.
that good?
Not quite, but heading very much in the right direction.
Okay.
Within 10%.
I don't know if you guys on Zoom heard that, but is it within 10% of optimal? How's it looking now?
That's pretty good. Is there any chance that you could tilt it up a little bit? Oh, that's great. Anybody else on Zoom want to weigh in?
That's perfect.
No, you're
Thank
doing
you.
great. Just okay. Thanks for letting me know that. What I think is best to do is not to keep looking at this one, but to look at a couple more that are just these just from previous exams. And I have to remind myself I haven't looked at this in forever. For a maximization IEP problem, branch and bound reaches the following point. So I was really feeling nice that year. What subproblems cannot possibly yield an optimal solution to the original main problem, even if they were elaborated further? So we know we can score 120 and we're trying to go up. So don't bother exploring underneath those two. If you stop now, what guarantee can you give concerning the best feasible solution identified so far in terms of being percent optimality? The very best that we could ever find would be this 150. So I'm looking for the 30 divided by 120 or 150. That's the point that I was making with you. So it's really 20% because conceivably Z star could be as big as 150. So this is guaranteed to be within 20% of the optimal solution value. But if you divided the 30 by 120 and said 25%, I probably said that that's fine. So the important concept is the gap is 30. And then that's, what is the 30 of? Is it 30 of the score of the incumbent? Or is it 30 of the best that Z star could actually be? And technically it should be the latter, but don't worry about that.
Where did 30 come from?
150 minus 120 is 30. We know how to do 120. The very, very best we could ever hope for is 150. The gap is 30.
Is this anywhere in the question we know the best? Okay, we read it that the best we can get is 150.
Yeah, because 150 is the largest of the LP relaxations of any of the leaves.
So without the constraint, the best thing we can get right now is 150. But we know that the IP solution, however, is 120.
The current incumbent solution, we know how to score 120. If we worked forever and elaborated everything, conceivably we could do as well as 150. And so that goes along with the classic kind of question I could ask is, what are the tightest bounds you can give on the optimal solution value for the original problem? Well, it can't be any worse than 120. We know for sure we can do 120. It can't possibly be better than 150 because nothing under here can beat 125, nothing under here can beat 115, nothing under there can beat 110. So the best we could hope for is 150, and we know for sure we can do 120. So that's the range of possible values for the unknown Z star.
Why in this case 150 is not optimal solution? Why is that
Well,
not like-
when we explore under here, it might turn out that the best thing under here only scores 88. We know that nothing under here beats 150, but the best integer solution under here might be much worse than 150. This is not an integer solution.
So we give 120 this crown because potential of 120 is.
Right? We know for sure we can score 120. We have a solution that is integer valued, so we can achieve 120.
So are we saying that was 150 is not integer?
Correct.
Oh,
This
okay.
is the notation. When you see ZIP equals ZLP, that means the LP relaxation return an integer solution. So we're done. That we stopped here. There's not a bounding issue. That's just done. We found an integer solution. Over here, one or more of the decision variables are non-integer, so we have the option of exploring further. And we may well want to, because if we explore further under there, we might do substantially better than the incumbent. Last part is, what constraint would you add to find the subproblems underneath here? So in the solution, the LP relaxation, decision variable x7 had a value 6.7, which is not integer. So over here, you would add x7 less than or equal to 6. And for that daughter, you would add the constraint x7 greater than or equal to 7. Yep.
Can you just, what wording would you use to answer B? Like it's 30% optimality or within 30% tolerance? Like,
Well, so the really truly correct answer is if we stop now, we can guarantee we're within 20% of optimality. Where did the 20% come from? The important thing I would like you to be able to recognize is the numerator of that, which is we can't possibly improve by more than 30. And technically what we should be dividing by is the 150. But if you actually divide it by the 120, I'd be like, fine, you basically, that's plenty good enough for an introductory class.
Yeah, so in this question is just coincidence that a problem 3, like in the same node, we are getting the other one, right? We could have gotten 150 on some other leaf on the road node on the right.
I mean, I'm not sure what you're asking. I can see that I'll never beat 115 and I'll never beat 110.
No, so if we had 150 as a ZLP for subproblem 6,
Yeah,
then we take 150.
100%, yes.
Okay, so it's not just for, we compare just the incumbent and the node right next to it, like.
Oh, absolutely correct. So there is a best incumbent, that's the best incumbent that's used for pruning throughout the whole tree, not just its first cousins that are nearby. For a minimization problem, we get to this point, which problems can be cut off. Whoops. Somewhere along the line, I lost. Getting worse, not better. Oh, I missed it. There's a delay.
Recording in progress.
Okay, I won't touch it again. For this minimization, which problems can be cut off? How do we know it's minimization? As we added constraints, numbers went up. That's bad, so I must want to go down. I have an incumbent that scores 320, so I know for sure I can get 320. And I'm trying to make things small, so there's nothing under here that will be smaller than 330. If the tolerance were 10%, then I can also cut off this one and this one because they can't possibly do more than 10 or 20 units better, and 10 or 20 units is definitely less than 10%. What is the tightest possible bounds that we can draw on Z star? Well, Z star cannot be worse than 320, and it cannot be better than 260. So you write 260 less than or equal to Z star IP, less than or equal to 320. So basically, how do you do these? First, figure out whether it's max or min. Then identify the incumbent. The incumbent is one end of the possible range of the value, optimally valued to the original solution. Then you scan across all the leaves and see which of the unexplored leaves has the best ZLP. Is that the biggest or the smallest? Depends whether it's a min or a max. That gives you the range. Okay, exam format. 5 problems. 3 are some form of short answer, like maybe one of them has a tree like this. And those are intended to just be, do you know the concept or not? In some ways, they're almost like testing, do you recognize a term and know the ideas that go along with that term? And that's about half the points of the exam. Then questions 4 and 5 are 2 very difficult formulation problems. So half the points in this exam are formulation. And these are not going to be like they would have been in the first exam, sort of write the Howey formulation where you're going to write max 350x1 plus 300x2. These are going to be ones where you have to have summation notation and to be able to write things in the abstract. So I could say something like, write out the general form of a product fixed problem, and you would say max z equals sum I equals 1 to n if they're n products times pi xi, where pi is the profit per unit and xi. So you're going to be writing in that symbolic notation. And the exams are cumulative, especially on those short answer concept kinds of things. But I'm going to emphasize the chapters since the last midterm, because what I want is all of the substantive chapters to contribute about equally to the final grade, and to make up for the fact that chapters 6, 7, and 8 have not been tested yet. Most of the points on chapters 6, 7, and 8 are most of the points of this exam are on 6, 7, or 8. Chapters 6 and 7 make really good formulation questions. There are 2 formulation questions. I leave it to you to connect the dots. And then chapter 8, we haven't gotten there yet, but the key ideas in chapter 8 are not formulation. And they are also really not problem types. I'll explain this on Tuesday, but when you get to nonlinear, you no longer have a half a dozen problem types that sort of span the space. Chapter 8 is a very different feel. In chapter 8, the emphasis is really on the algorithms. So with simplex, yeah, I told you a little bit about it, but it just works. So you didn't have to know much. Hit return, magic happens, yay. For branch and bound, there were some things you had to know. Like you had to know that running common functional tolerance looks like that. And it's nice to start it with blue cells that are feasible and pretty good. That's about it. But when you get over to chapter 8, there's no one algorithm. In fact, next week, we're going to talk about, I'm not sure how you count, call it 5 or 6 different categories of algorithms that are meaningfully different in how they operate and meaningfully different in what problems they are well suited for. And it's more difficult now. The kind of problem they're well suited for will be their mathematical structure, as opposed to, is this a factory problem or a hospital problem? Anyhow, so you know the exam's going to have to cover those ideas, and it's not going to be in the formulation area. So, you know, connect the dots. I think you probably have a pretty good idea. I'm not trying to really surprise you. It's going to be a hard exam, unambiguously, but I'm not going to try and make it hard by sneaking in some Aristotle. People asked, how can I use the old exams that are on Canvas to prepare for it? And absolutely, use them, take them under time conditions. But a couple of caveats or explanations. There are probably 10 years worth of exams on Canvas. The course has evolved a little bit over time because the field has evolved some over, well, actually the field has evolved a lot, but an introductory class that has only medium-sized ramifications for us. So if you look back at the old exams, they might have put more emphasis on chapter 4. Over time, we reduced emphasis on chapter 4 to free up time for other things, for instance. One of the big changes is that up until 3 years ago, there was only one midterm and a final. So the final was covering often more, double covering more than just chapters 6, 7, and 8. So the older exams might have had more on chapter 5. COVID messed with us in a big way. So 2020, I think, was not really a COVID year with respect to the final. I think we shut down the campus like 5 minutes after the final was given. So I think the 2020 exam is not a COVID exam, but the 2021 exam, we were in distance mode. So that just meant the nature of the exam was different because it was hands on the keyboard and distance. Last year was a tough year for a whole bunch of reasons that I don't need to go into, but the ramification was I had to dial back the difficulty of the course last year. So last year's exam was notably easier than what you're going to have next week. So it's not deceptive. There's nothing wrong with using last year's exam, but if you look at last year's exam and think, then go ahead and take the 2020 exam. What's that?
No, that's exactly how I felt up, like attempting both the exams last year and seeing the exam paper after hours.
You guys are just brilliant. So, you know, the dean said I have to make the class harder. Something like that. Questions on format of the exam?
Do you give an example with the what do you mean by term and recognition problem? That the beginning of how long we term and
Sure. So an example of that kind of question would be, how many decision variables are there in transportation problem with 5 sources and 8 sinks? All right, and so if you understand what a transportation problem is, you say, oh, there's one decision variable for every arc, and there'd be 5 times 8, 40 arcs. So the goal there is to ask a question such that if you know the answer, it doesn't take you very long to write down the answer. And frankly, it doesn't take the TAs and me very long to grade, but that if you don't know the concept, you won't be able to answer it. So that's kind of, to my mind, a good kind of test question on a test where inevitably, I would love to give you a 4-hour-long exam. So we could ask about everything we've covered. You would kill me, but I don't want, the formulation questions have to be time consuming. There's no other way around that. But the other ones, if you really, really know the idea, the other ones should be pretty quick. Okay. Newspapers. I'm just going to do 2 more of these goal programming problems because, you know, the good thing about chapter 7 is at some level, there's ultimately almost like just one core idea. There's several pieces of it, like mini-max is a cool idea and undershoot and overshoot is a cool idea. But absolutely, in chapter 7, it's just keep looking at examples, and at some point you'll go like, oh yeah, I know what we're doing. I've seen this before. So we'll do 2 more that are slightly bigger problems, so they're a little bit more interesting. And then a lot of people are interested in environmental issues. So the backstory here is we operate a paper products recycling plant. So we have 4 different feedstocks, and we're producing 3 kinds of products. So Xij is going to be tons of feedstock I we use to make product J. So it has kind of a transportation feel to it because it's double subscripted. And I'm not sure where it is in the, yeah, so we have an order for 500 tons of this, 600 tons of this, and 300 tons of this. So there's going to be a kind of a sum down the columns thing, and we have to produce at least that much. A little bit like a make versus buy, minimum cost way of meeting demand. The twist relative to things we've done in the past is if I use 1 ton of newspaper to make newsprint, I don't make 1 ton of newsprint. I only make 0.85 tons of newsprint because there's loss. And so when we have the equation that says we have to produce 300 tons, I think it is 500 tons of newsprint, it's not going to be X11 plus X21 plus X31 plus X41 greater than or equal to 500. It'll be 0.85 times X11 plus 0.9 times X21 plus 0.9 times X31 plus 0.8 times X41 that is greater than or equal to the amount of this that we have to produce. There are limits on how much of these things we have, and for that you are just straight up adding across the row. You can't use more than what you have available. So that's like the physics of how you run the recycling plan. Oh, and the other part of the physics of the recycling plan is along with every Xij, we produce sludge. And you can guess we want to minimize sludge. So sludge is pollution, bad thing. And so there are CIJs that are costs, like we normally have with a transportation type problem, and that's one objective. But then there are these other IJ things, call them SIJ, amount of sludge produced per ton of feedstock I that's used to make product J. And our second objective is to minimize sludge. Questions about the problem we're trying to solve? And this is I kind of like this problem. It's not quite a case, but it has a fair amount of richness. You have to really have the physics of the process that you're managing, and it's a really natural one for multiple objectives. Maximize profit, minimize dollar cost, but also minimize sludge production. If the company, this company, just paid its garbage service delivery $10 per ton of sludge to cart away the sludge, then you wouldn't have to do this as a multi-objective problem. Then you would just instantly convert everything into dollars and you do it as a single objective. But it is very possible that the company can't do that because although there may be a specific dollar cost associated with disposing of sludge, there might also be a public relations penalty associated with sludge production that isn't so easy to monetize. And that would be an argument why it might want to not collapse everything down into dollars by monetizing sludge production, keep them as separate goals. So this is a template for solving the problem. And admittedly, this once you have the template, this is a pretty straightforward problem, and it's not a trivial thing to get this all organized in this way. So if you are thinking, oh my goodness, it would have taken me 45 minutes or more to get from those words to something, yeah, it took me that long too. So I'm done this because I want to emphasize what we're going to do with the undershoot, overshoot, and so on. But yeah, it takes a little work to organize stuff. Is that a question?
Yeah, but it's a technical thing. I was wondering, do you know how to turn these on to see that or no?
No.
Okay, no worries.
Okay, so let me just put some numbers in here so that it's not all zeros. So that's the equation for production that I was referring to, factors in these yield rates, whereas the amount used is a simple sum across. The straight up costs are, these are costs on the IJs. There are sum over I and J, meaning it's a rectangle. These costs times our XIJ decision variables, but then there's also a purchase cost for each of the feedstocks. And so the cost per ton used is going to get multiplied by these row sums. But when you set it up that way, now my cost, the one cell that I care about, is just the sum product of the whole yellow rectangle, including column E, times the blue rectangle augmented by the sum across those rows. In algebra, you could write that as summing over the feedstocks, of which there are 4, and summing over the products, of which there are 3. There is a CIJ, that's the processing cost, that's double subscripted, and then there's a purchase cost. I don't know, we'll make it, I don't know, capital C would be the purchase cost, and that's single subscripted because it costs you the same amount to purchase a ton of this feedstock, no matter which of those 3 products you use it to make. And then sludge is even simpler. Sludge is just sum over IJ, a coefficient times the XIJ. We've already used C for cost, so we use S for sludge. So those are our 2 G's. So this is G2 of X, and this one is our G1 of X. One thing we care about, second thing we care about, can't point solver to both, so we have to do this as a GP. And I already have targets there. You don't remember. I hope those are just the right targets. Well, we can check it. I'm gonna minimize costs and see if we get 44068. So to find a target in a multi way, you just focus on one of the objectives completely, giving it all of the regular decision variables and all of the usual hard constraints, like don't use supplies that we don't have, and make sure that we produce enough. And there is one of those places like back in Weed Whacker, could be equal to, could be greater than or equal to. Everything is costly. So even if we did this as greater than or equal to, the objective would push stuff down so it's satisfied as equality. And I think that's it. Am I forgetting something? Yeah, so I just optimized on that cell G18 alone, paying no attention to sludge, and that turned out to produce this target. And I should record in my table this as something that we can do. And now I will put solver on sludge minimization duty. And yep, that's, so the targets were correct. Probably really meant to have deleted them so that we had to rederive them. That pre-step finding the targets is like the mold. Then to turn it into a GP, we do the automatic pilot, what you get plus undershoot minus overshoot is the left-hand side of the soft constraint. And what we're really focused on is percentages. So the deviational variables divided by the target gives us the deviations in percentage terms. And the problem says minimize the maximum percentage deviation, and then we're going to impose a particular pair of weights. But initially, we're just going to minimize maximum percentage deviation. So now we're in GP mode. So we no longer are pointing at either of the specific G1 or G2. We're pointing at some overarching meta objective that puts downward pressure on the deviations. In minimax Q, that is just the plain old Q. We do have to tell solver that the deviational variables are honest to goodness blue cell decision variables, as is Q. We have to add to the formulation the soft constraints, left-hand side equals target values. And then we have to connect the percentage deviations to the Q. That's connecting a sheet of plywood that we're trying to push down to the posts and saying you can't push the plywood through the post.
I think you said the left-hand side equal to the left-hand side instead of.
I did. Wait. I mean, if you're gonna be dumb, go for it all and be really dumb. Thank you for catching that. That would have taken me a long time to find. All right, that looks better. Let me expand the digits here so we can see more clearly that magical mystical Q did its thing. It balanced the underattainment on those two objectives. And now we have a third point on the efficient frontier, which I'm starting to create here. Where's the smiley face? Yeah, we don't like cost and we don't like sludge. So smiley face is here, and those efficient frontiers will go towards the smiley face because of diminishing returns. So the very first thing we did was minimize cost. That would have been that dot. Second thing we did was minimize sludge. That would be that dot. This is the most recent dot that we created. Why did Ragsdale say determine the solution that minimizes the maximum percentage deviation? So the TAs have something specific to grade, right? So that question has as its answer that dot. So we can grade it. What do we really care about in the real world? We care about seeing the whole frontier. So what you want to do is be able to generate more dots. To generate more dots, we have to add weights so that we have weights that we can twiddle with. Ragsdale takes us a step in that direction by saying, suppose management considers minimizing cost to be twice as important as minimizing the amount of sludge. What solution does this suggest? Honestly, that question is irrational, non-specific. It makes no sense. if you take the fall class from me, you'll learn this idea. You can't talk about some broad thing being twice as important as something else. It's really only sensible to talk about swings in the amount of pollution, a specific swing in the amount of pollution being twice as important as a specific swing in the amount of profit. This statement, oh, I'm sorry, it's the other way around. This says cost twice as important as the amount of sludge. It's some very superficial sense. You'll hear people say this all the time, but suppose that the change in cost were a penny. Do you think they still think that that is twice as important as a very big change in the amount of sludge? No, it's a nonsensical statement. Why is it here? Just to give you another specific thing you create that the TAs can grade, but getting to that is also how we get to the apparatus for tracing out the whole curve. So we have to add weights, and we're gonna dislike overshoot in particular. And the statement is the cost overshoot is twice as bad as the other overshoot. So then we multiply those weights by the straight percentage overshoots to get weighted percent overshoots. And now we just change the rule about plywood and fence posts to say that the plywood can't go below these weighted fence posts and or pillars instead of the plain ones. So I'll go back into solver, find the constraint that was comparing things to Q, and change that so it's the weighted percentage deviations against which Q is constrained. So we solve again, we have a new solution. Before I put it on the graph, where is this dot going to be compared to the dots that we already have? So the most recent dot was here. Now we're putting twice as much emphasis on cost minimization. Is this fourth dot going to be to the left or the right of the third dot? Yeah, it's going to do better on cost. So that's what is the end of answering the Ragsdale question. In the real world, we would change those weights some more. Every time you change the weights, you get a different dot, and you would do that until you kind of filled in that curve to a reasonable degree of precision.
And we don't put numbers on the undershoot because we don't care about doing, reducing cost and reducing sludge. Like that's, I mean, we do care, but like that's a good thing if you undershoot. That's why you would.
Yeah, I like the latter sentence better than the first sentence. It's fantastic to go under on cost and sludge production, so you want to put zero penalty on them. In some respects, I probably should throw you guys the curveball of what does the efficient frontier look like when the goal is to hit a specific value as opposed to just max or min. But then the concept of the frontier changes. It becomes more like the smiley face is in the middle of the diagram, not in one of the corners. And the efficient frontier is then going to be in some sense like a circle, won't be literally a circle, but a figure around the smiley face and showing how close you can get to the smiley face, but you potentially approaching it from all sides. It's easier when it's all the objectives are just more is good or less is good, because then the smiley face goes into a corner of the diagram.
Would that little circle be where you're trying to minimize one goal, maximize another?
Well, no, most of the time the goals are just max or min. And like a classic exam question, but I didn't do it, is I can say something like, you're responsible for a production process that makes diesel boops and gobby bombs. And Hazel boops are bad things and Gabi bombs are good things. What does the trade-off curve look like? Well, smiley face in that case would be in the upper left. The efficient frontier would bow towards it. It'd be impossible to be there, so that's infeasible. This side is suboptimal. So that's a classic kind of question. When these goals are simple max or mid, then the smiley face goes to a corner. The more complicated thing, which I did not give you guys this year, so it's not going to be on the exam, would be to say the smiley face is here. Like you want 172 Hazel bops and you want 83 Gabi bombs. That's exactly where you would most like to be, but you can't get there. So now the frontier will sort of wrap around it, and everything inside is what's infeasible. Everything outside is suboptimal. And then you ask the boss, which point on the frontier brings you the most joy? But so the concept isn't that different, but this is definitely easier to think about. So this is usually all I do in an introductory class.
Probably a dumb math question, but why can't we draw the physical region as we did before?
What are the axes? The key difference now is the axes are what we achieve, not just the x. There might be 20,000 x variables here. And that's the power of this, right? It's very common for the optimization problem to have 20,000 x's. We can't draw 20,000 dimensional space. We can't think about it. But when you translate it into the axes are labeled in terms of attainment on what the executive wants, it's really common for there to be important problems with only 2 or 3 big driving outcomes, even if there are 10,000 x's.
Okay, so it's like literally, we could, as huge, therefore we would only do the outcome and draw out the outcome, and then the big guy can choose.
Yep. Yep. We, the analysts, understand 10,000 dimensional space defined in terms of x's, but the boss isn't as smart as we are. So we're allowing the boss or the public in a public policy problem to think about things where the numbers pertain to the outcomes, what we care about, not the grubby details about how we produce that outcome.
So we do the hard work.
Absolutely. The analysts always do the hard work. That's why you came, because you want to do that. Literally, it's only 26 minutes left. I don't think I should do these. I want to open it up for general questions about the whole course. If you've got none, then I'm happy to go on and do the next case. But
This is about this question answer. This is like a comprehension check. When we're using the unweighted Q method, is our objective function to minimize the biggest deviation for one of the decision variables?
don't say
Or
decision
both
variables.
Yeah.
Exactly. It's
But not-
minimize the maximum percentage deviation. How do we mechanically do that? We minimize Q with those constraints. So, but that's good review. So let me write that down, get to a different color. So what's the algebraic formulation of one of these minimize maximum things? The objective is just Q. We're just pointing to that one cell, but then we add the constraint that for all goals I, the Q is greater than or equal to the undershoot, usually expressed as a percentage. And also the Q is greater than or equal to the overshoot, again, customarily expressed as a percentage. But sometimes I'll be nasty and say something like minimize the maximum percentage undesirable deviation. And then you have to slow down and do that thought process. Oh, wait, if I undershoot on cost, is that a problem? No, it's not. And then you would open it. So the two kinds of objective functions in chapter 7 are that one, or just minimize sum over I, Wi minus Di minus, sometimes divided by Ti, plus Wi plus times Di plus, often divided by Ti. Yeah, sure. So that's one kind of chapter 7 objective. The other one is minimize z equals sum over I. And the I again is going to be indexing goals. Not indexing products in a product mix problem or customers or anything. These are, it's indexing goals. And you have a weight associated with each of the undershoot variables. And commonly, we do that in percentage terms. But that's sort of a convenience for us in interpretation. Whether or not you divide by the TI isn't really changing the mathematical structure. Yellow times blue and yellow divided by yellow times blue are both the same mathematical structure. And because these W's are not specific numbers, we're just going to play around with them and change them. It doesn't matter whether or not we play around with the W's or we play around with the W's divided by T's. Either way, what we're trying to do is find the frontier. In fact, let me say this point too. Whether you do this or you do that, you're trying to find the same frontier. The frontier is an object defined by the physics of the problem. You don't know where it is. What you're doing in chapter 7 is being like an explorer. You're trying to discover where is that frontier. And those are just two different tactics for finding the exact same object. The object is a real thing that does not, somebody asked in one section, what's the equation for it? There ain't none. There is not an equation for it. It is defined implicitly by all the physics constraints and parameters stirred together in that optimization formula. And your job is to bring that surface to life. Last fall, in Lowell Taylor's class, he would say, here's the production possibility frontier. You said, great. But if you ever think, where did that actually come from? It comes from this kind of stuff. We're learning how do you mechanically compute those frontiers that until you come along, nobody can know where they actually are quantitatively. That's a very important thing to be able to do.
Professor, any of the goal programming problems can be formulated with both objectives, right?
Yes. So you as an analyst, so in a textbook problem, do what the textbook question says. Or next week, do what the question says. But absolutely, in real life, you can do either of these. All right. Next thing I'm going to say is not on the exam. It's not one of those. It's more like a second-year idea. This approach will tend to hang only on vertices. This approach actually allows you to find points that correspond to being in the middle of a facet. So this approach actually is a little better at really filling in the frontier and not having dots with gaps between them. So I at least tend to like this approach better, but that's totally beyond first year introductory class.
This also kind of might be a dumb question, but
No dumb
what
question.
would be the verbiage on an exam for us to like cue to distinguish when to do which? I feel like-
Minimize maximum percent and minimize max,
Okay.
and then minimize weighted sum. Those are the keywords you're looking for.
There's no like data table functionality for changing weights.
Fantastic question. It's not literally a data table because the data table just plugs in the numbers, and what we want to do is plug in the number and then run solve. Okay. Every good optimization software package has that capability. Up through the 6th edition of the textbook, Ragsdale provided an add-in. It was basically just a macro, but that actually creates security vulnerabilities on the computer, so he stopped doing that. And for that and other reasons, he switched over to saying, let's use the analytic solver platform instead of just basic Excel. And I understand why. Analytic solver platform has capabilities that just Excel solver does not, and that's one of them. My experience teaching, though, is that analytic solver platform greatly interfered with the ability to learn. And the reason is because it just has all these options out there. So the menus are cluttered with a lot of things that we don't want to distract ourselves with in an introductory class. If analytical solver platform were the only optimization software of industrial strength, then maybe I would think the best thing teaching wise is to get you used to that ugly, cluttered, inelegant set of options. But in reality, there is no industry standard for true advanced optimization packages. It's not like there are 200, but there are a dozen. And so I judge an introductory class, it's easier for us to stay focused on the concepts, not using one of those packages. But what do we give up? We give up essentially the data table with optimization capability. So you just mechanically do it 5 or 6 times and find some dots.
Just checking, there's always one unique. There's always one part of the frontier.
For any given set of weights, you will get one dot. But when you change the weights, you'll get a different dot. The way that you get to the unique one is if you just say minimize maximum with no weights, which is implicitly the weights are all 1, and then yeah, that will correspond to 1 dot. And why does Ragsdale ask about it? Because then everybody in the class will find the same dot that she is.
Oh, so they're saying the mini max version.
No,
There are 2, yeah, the Q method is.
so this one, they'll always say has W's. Here, Ragsdale will often ask about this one, but that's just the special case where the W's are 1. So the textbook question will often just say minimax, and that's only a single dot. But in professional life, I want to find the whole frontier, so I just insert the weights, and then I repeatedly minimize the maximum weighted percent deviation so that I can trace out the frontier.
But it's a little different because you're not summing all the deviations in the menu.
It is a correct statement that you're not. Yep.
So that gives you a different solution.
Oh, right. So for a given set of weights, which dot you get would be different whether you minimax Q or minimize weighted sum. But again, the weights per se don't mean anything. We just try a bunch of them to trace out the.
I'm just trying to understand like how they're connected. And you'll get different solutions between those strategies.
We got plenty of things that are hard to think about. Don't worry about that. Just, the weights are just a means to an end. We're just going to futz with them, twiddle them, try a bunch of different weights because we want to find a bunch of different dots on the curve. I mean, the only way that there's really meaning is if you got to the situation where you had a lot of dots over here and you want a dot over there, then I want to crank up the weight on cost because that'll tend to give me dots on that part of the curve that I haven't yet.
Can we draw
Explored.
any curve based on the weighted sum?
You want to find a dot with the weighted sum formula? I'm happy to give you a dot that way. So here is the weighted sum objective. It's the sum product of weights and percent overshoots. And now I just point solver to that. And I should disconnect Q. Oh, for those weights, I ended up going right back to the second one that I found.
Oh,
So that's sort of a coincidence.
I see.
But this is, in general, that's the other objective. That's this objective. And it's sort of by coincidence. The dot I just found happened to lie on top of the dot that I had already found.
back, and then you find the same two dots somehow. then
That
it's the same
one was
curve.
coincidence.
Yeah,
But the overall process is twiddle weights, repeatedly solve, trace out the curve.
it's actually the same formula. In a way.
Yeah, the only thing that's different is which cell is my objective. With Minimax Q, it was K15. With minimize sum of the weights, it's H13. And when you're doing this guy, you don't need these. That's why when we write these customarily, we put these constraints right under the objective, because they're like almost part of making the objective do what it's supposed to do. So that literally that's the objective function, but you need this. So that's serving the same purpose as this. But the soft constraints are the same either way. What you get plus undershoot minus overshoot equals target. And of course, the hard constraints are the same either way.
So the difference is, what do we care about more? Do we care about undershoot, overshoot more, or do we care about the weight?
You want the truth?
Yes, we-
Like that's a line from that Jack Nicholson movie, right? So the truth is, I care about the curve. And however I get the curve, that's great. So there's two different ways of getting the curve. That's what I really care about. Now notice the other half of the truth. On average, in a class like this, 90% of you can understand this, and 60% of you can understand this. I would hate to have you think you can't find the curve because you can't understand this, because you can find the curve with that. But for reasons I just talked about, if you understand this, I kind of like it a little bit better because it can find points on the curve that correspond to points that are on a facet of the feasible region. This one is only ever going to find points on the curve that correspond to vertices. So in that sense, this one maybe is slightly better, but it's definitely harder to learn. So if you understand this, but not that, you can still do goal programming. The other nice thing about this is there is such a thing as a problem where you want to minimize the max or maximize the min, and it's not a chapter 7 thing. It's just what you want to do. So learning the little minimax Q trick, it's a nice trick to know.
Yeah, so is it wrong to say that really the practical difference between when you use this is when you already have target values, you use a GP, and when you don't, you have to use the mult?
So I think that's a true statement that follows just from Ragsdale's definition of mult. Ragsdale's definition of mult is essentially, you don't know the targets, do this other pre-stuff first, find the targets. Ragsdale also does sort of say, this is the objective for mult, and this is the objective for GP, but I don't think the rest of the world thinks that way. I think the rest of the world thinks there's GP mult, and you can do either of those, and the rest of the world doesn't have that idea that this is a multi thing and this is a GP thing. They're both just tools for finding the curve. And the really important idea is repeatedly solve for different ways to find the curve. And Ragsdale makes a bigger deal of mult versus GP than a lot of people do.
So are you saying that you could also use GP to find target weights?
Totally. I mean, I can find the curve using this. Just repeatedly change the weights and re-optimize every one. You find a point on the curve.
But this is just a more efficient, mult is just a more efficient way of doing that. If you already have a target in mind, it gives you an optimal solution that you can.
I mean, I can do this if I don't initially have target values. I still just do that pre-step to find the target values.
Oh,
So
okay.
the have or not have target values is part of what Ragsdale connects to mult versus GP.
Okay.
But like, yeah, if I don't have target values, I can find them. And likewise, I can use either of those objectives.
When you talk about a facet of the feasible region versus vertices, what is that?
That's back to chapter 2 language. So think about now in X1, X2 space, every one of the constraints creates a hyperplane in general, an n-dimensional space, an n-1 dimensional hyperplane slices the space in half. A vertex is a corner and a facet is an edge.
So you're saying that
This approach will only stop at vertices.
in terms of like the solver.
Yeah, and so there are points on the feasible region that correspond to points on the facet.
Yeah.
And this guy can stop in the middle of a facet. This guy will essentially just jump from vertex to vertex. Cool. There were 6 other chapters or something like that. So, questions about anything else from the course?
So do you like this cube better than the weighted sound? Is that because that you can apply the cube to other stuff, but the weighted sound can only works with the current problem?
Yes, that is one of 2 reasons why John prefers this as well as chocolate chip ice cream. Right?
Okay.
So yes, I mean that just that minimize max thing is kind of cool. And so this is a nice bonus. And then the second reason why I prefer it is this idea that I sometimes want to be able to fill in between dots more by being able to stop in the facet. But I want to go back to the statement that, because I know there's some of you out here who are like, I hate you. I never liked James Bond. I hope I never see this again. It's fine. You can still do goal programming. You can still find the frontier. So I think it's not a bad thing that an introductory textbook still does this. This is easier to understand. Historically, this came first, and this lets you do goal programming. So that's like bonus. That's the cake, that's the frosting.
Would you mind maybe going over again, algebraic notation for auxiliary variables like big N and the binary auxiliary variables for?
Yes, no, I'm happy to do some of that. That is also one of the asynchronous lectures. So if you want to see more of that, it's the second asynchronous lecture from last week has that material. Auxiliary variables are a general purpose tool, the same way like adding a fake arc or a node is. So we have to be more specific about which of the things are we going to do with them. Is it a fixed cost? Is it a minimum activity level? Or is it a quantity discount? Those are the 3 things that we covered in this class that you can do with auxiliary variables. We'll start with fixed cost because it's definitely the easiest of the 3. They get harder as you go on. So the idea of the fixed cost is we're trying to create a feasible region. And I'm sorry, not a feasible region. This is, the picture looks like this. So as a function of the amount of the activity that we do, whatever that activity is, making hot tubs, shipping stuff down an arc, courses taken, whatever, there is a constant per unit cost, $2 per unit, but in addition, if you do any at all, you have to pay that fixed cost. So that's what we're trying to model. And you cannot do that in a linear program. It's just mathematically impossible. But if we have binary variables, we can do it. And what we do is minimize the fixed cost times the binary indicator variable plus the marginal cost times X. So X is continuous and this y is binary. If we stop there, solver says, I know how to minimize cost for you. I'll just make y be 0, no matter what x is. So what we have to add is we have to say, if x is positive, then make y equal 1, otherwise y equals 0. That would be a valid Excel formula, but that is not linear. We'll talk more about this next week with nonlinear programming, but that's a nonlinear function because if I were to graph that if function, it basically looks like this. It's just either 0 or 1, false or true, and it's got that step up. That's not linear, so we couldn't run simplex. It is also a kind of nonlinear that is just brutal for the computer. No reason for you to know that yet. That's an idea for next week. But the if function is not linear, and it turns out it's not linear in a really, really nasty way for the computer. So we do something that looks kind of strange. We add this constraint because that does the same thing as the if function, but it's linear. This is blue. This is yellow. This is blue. So on both sides, we just have yellow times blue. Here, the yellow is 1. So that's linear. How does it work? Well, if you want x to be 0, then y is allowed to be 0 because it's a true statement that 0 is less than or equal to some constant times 0. So this permits us to be here. And the fact that solver is trying to minimize y will ensure that it makes y be 0 when it is possible. But if x is 5, the only way 5 can be less than or equal to some constant times a binary is if that binary has flipped up to be 1. And then that's saying it's like here. And we will charge ourselves that fixed cost. So this is an equation. It's a linear equation that plays the same role as an if statement, and it's making the y variable behave itself. The only remaining question is, well, what's m? If it's yellow, it's got to be a number. Should it be 7? Should it be 23? Should it be 614? And the answer is, we want it to be large enough that we don't put an artificial cap on x. There's no physical limit on x in this problem. So we want to choose m to be big, as it's called big M. But if you just make it 999999999999999, you'll actually create some sort of round off errors for the computer. It causes trouble for the computer in a different way. So the way we mathematicians treat this is we leave it capital M. In honest to goodness, the technical name for that is big M. But like I joke about the magic theorem, I'm the only person who calls that the magic theorem. But big M, that's actually the real mathematical terminology for that idea. And what it means is just make M be big enough to not put artificial constraints on x, but no bigger than that. And 15 years ago, we would have spent most of a class period talking about, well, how small can we make that to help out the computer? Computers are great now. So we now don't worry about it very much. In practical matter, you could just try 9999. If after you solve it, you find the x is also 9999, meaning the m is binding it, then you didn't choose a big enough m, you just try a bigger m and solve it again. I gave you hints of how one thinks about trying to make m be small. For instance, if x is the amount of electricity produced by a particular generator on a particular day, then you can make m be the maximum amount of electricity that that generator can produce. Because you would never want x to be bigger than that anyhow. 15 years ago, we would have spent an entire 80-minute class talking through some of those instances of reasoning about how small we can make them. But the important concept these days is just this, and not putting as much emphasis on using the smallest possible big M that's big enough. All right, so that's one. That's fixed costs. Does that make sense?
And when you're adding complexity to those type of problems, you're just doing the same thing over and over again, just like adding more like X1, X2, and.
So for quantity discounts, that's the one where we do the trick of we divide the X into two pieces. Right. So the per unit cost is high for a while and then it's low. How do we handle that? For that one, we do the trick of dividing the overall X up into X1 and X2. No, so let's pick X. What's your favorite thing in the world? Object.
Oh, kids, I guess.
Oh, no, I don't want to go there. I don't want to have a factory making kids, but I love your answer. That's heartwarming. But how about we'll do binkies, right? Because if you like kids, you really like binkies because they help you sleep. For those of you who are not native English speakers, binkies are those things you stuff in a kid's mouth when they're crying so you can get to sleep. You probably have a sweeter way of explaining it, but that's what they were for me. So we have a factory and we make binkies. And the first 5 binkies are expensive to make. They cost $4 per binky to make. After that, the cost drops to $1 per binky. So then instead of having a decision variable X, how many binkies we make, we have 2 decision variables. X1 is the number of binkies we make at a cost of $4 per binky. X2 is the number of binkies we make at the lower cost of $1 per binky. So to handle that quantity discount, that's the trick that we use. But we do have an auxiliary variable because if I just say, hey, minimize 4 times X1 plus X2, solver is going to want to immediately start buying binkies at the lower price. So we add this constraint that says X2 less than or equal to big M times that binary variable, and X1 greater than or equal to 5 times Y. And those 2 equations together implement the if statement. So this says, if you want to buy any cheap binkies, we're forced to have that binary variable become 1. And as soon as the binary variable is 1, this says you had to buy at least 5 expensive binkies. So the overall concept here is integer optimization problems are much harder for the computer. That's that branch and bound thing. Also true that nonlinear is very hard for the computer. That's what we talk about next week. Integer and nonlinear is just fatal, because the computer will not be able to solve the problem. So we, the human beings, have to turn backflips to figure out how to implement things like an if statement using only linear expressions. Because if we're going to have integer, we better keep everything linear. And yeah, it's totally strange. It's weird, it's counterintuitive, but the motivation is we're trying to keep everything linear. Sorry I went over. Have a good weekend.